Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. You know, one of the things that I wanted to do when I started this channel was demonstrate that any of us can do science if we just want to make a little bit of effort. Now, recently I went on vacation with my family. We traveled from Michigan to Panama City Beach, Florida. And I thought it was a good opportunity to do a little bit of science. And this is stuff that you guys can do. All you have to do is just get a little bit of equipment, and you can find some interesting things. Now here's the problem I decided to look into. I have this scale and these two reference weights, and as you can see, the scale is calibrated in my office to measure 1,000 grams for those two 500-gram reference masses. Now my office is located in Michigan at approximately 44 degrees north latitude. Now for example, at the equator, the linear rotational speed is about 1,038 miles per hour. Here at 44 degrees north latitude, it's about 735 miles an hour. Now the interesting thing is, if the Earth is indeed rotating, we could predict that an object that weighs 1,000 grams at my office at the 45th parallel will weigh less than that in Panama City Beach, which is at the 30th north latitude. Because the rotational speed of the Earth is faster at Panama City Beach, and as a result there's more centrifugal force. So let's go ahead and have a look at the experiment that I conducted on my recent vacation and see whether or not the Earth is indeed rotating. So let's cue up the music and get going. Okay, so let's go ahead and have a look at the procedure here. What I did was I got a precision scale, and here you can see it right here. There's the model, and this is the 3,000 gram capacity model. And the accuracy of this scale is down to 1/100th of a gram. Now, as you can see, I have two reference masses, and these are 500 grams apiece. And as you see, I've calibrated the scale in my office in Michigan to read 1,000 grams. And then what I would do is I would go ahead and I would use my phone to determine the latitude and longitude of where I took this measurement. And as you can see, this is 43.6 degrees north latitude. Now the final part of this is the route that we took. As you can see, from central Michigan down to Panama City, there are two basic routes that you can take. There's an eastern route through the mountains that goes through Knoxville, Tennessee, and takes you down to Panama City. And then there's a western route down 65 that goes through Birmingham, Alabama, and is a little less elevation than this eastern route. So what I decided to do was that we would go down the eastern route going to Panama City, and I'd stop by and see a friend of mine in Tennessee, and then we'd end up in Panama City Beach. And we'd return up 65 via this western route, which had a little less elevation. And every 2 degrees or so of latitude as we went down, we'd stop for gas, a snack, and I would plug in this precision balance and I would weigh my two 500-gram reference masses. And I did that all the way down to Panama City Beach. Then we had our vacation, and at the end of the week, when it was time to come home, I went ahead and calibrated the scale again to 1,000 grams. And we returned home, again checking measurements every 2 degrees all the way back home. Now the total distance that we went was 13.5 degrees. Now other than the fact that we planned on overnighting in Knoxville, Tennessee on the way down, we didn't really have any plans for where these stops were going to be. We had no way of knowing where they would be in advance. Likewise, when we returned home, we ended up staying the night in Elizabethtown, Kentucky, but we had no idea where we were going to be stopping and making these measurements on the way back. The key measurements were the calibration to 1,000 grams at the start of the trip, and then whatever we had at the end of the trip. So let's go ahead and go over some of the numbers. This is the trip from Michigan to Panama City Beach. Now, it was initially calibrated up in Mount Pleasant, Michigan to 1,000 grams. There is the latitude And right there is the elevation above sea level. Now, I've also put the temperature in Mount Pleasant that day. It was quite a warm one. It was 28 degrees centigrade or 84 degrees Fahrenheit. Now, notice that I haven't put down any other temperatures. There's a reason for that, and that'll be revealed a little bit later. I do have those temperatures. But here's the interesting thing. As you can tell, most of these altitudes are about the same, except for this one, which, as I recall, was Knoxville, Tennessee, a little bit more up in the mountains. But they're all around 800 feet above sea level, so there's not a whole lot of change in altitude. Now, what there is a change in is latitude. We go from 43.6 down to 30.13. The other thing that we see a change in is the measured weight of those same reference masses on the same scale. They were calibrated to 1,000 grams in Mount Pleasant, and by the time we got down to Panama City Beach, they had lost 1.53 grams. Now, the purpose of this experiment was to demonstrate the rotation of the Earth. As you know, gravity pulls us towards the center of the Earth. As the Earth rotates, there's centrifugal force pulling us away from the Earth, and that's perpendicular to the axis of rotation. While it's 1,038 miles per hour at the equator, when we get up here to Michigan, it's about 735 miles an hour. The result of this is that there is less centrifugal force as you get towards the poles than there is as you approach the equator, and this is both the North and the South Pole. Now, this centrifugal force corresponds to objects weighing more as they get closer to the poles than they do as they get closer to the equator. And that's exactly what we're seeing demonstrated in this experiment. We calibrated the scales in Michigan, and we drove them south 13.5 degrees, and we had a corresponding decrease in weight as the centrifugal force increased as we approached the equator. Now, this is the expected finding. Likewise, if we calibrate the scales in Panama City Beach to read 1,000 grams, and we drive them north, we would expect the reference masses to measure a higher weight as we went north 13.5 degrees. Let's go see what happened. And again, we were at 30.13 degrees, 16 feet of elevation, and as I mentioned, we calibrated the scales to 1,000 grams. Those were the two 500-gram reference weights. And this was, again, done several times for consistency. And then we proceeded north along that western route up 65. You see the latitudes, and you see the corresponding measured weights of these two 500-gram reference weights that were calibrated in Panama City Beach at 30 degrees north latitude. By the time we got back up to 43.6, we had gained 1.16 grams. So clearly, this is not related to going north or south, and while there are some changes due to elevation, we are seeing significant changes due to changes in latitude. Now, in order to understand what we're looking at, we should have a look at what these weights were predicted to be based on a rotating WGS-84 geode. Well, let's go and see if there are any tools that we can use to predict what the weight should be. So let's have a look at this calculator put together by Walter Bislin. So this is the centrifugal and gravitational acceleration in an aircraft calculator. It's quite a long name, but it does seem to make some sense. So here's how we put it together. So I put in the calibration data. So we were at 43.6 degrees north. We were at 778 feet MSL, and we were calibrating to 1,000 grams. So we put in 1,000 units. Then what I did was I went ahead and I put in the latitude of Knoxville, Tennessee, which is where we did one of our measurements. As you see, that's 35.84, and it's 1,004 feet. Now, according to this calculator, it will predict that that scale will register 999.3731 units. Now, we can only read out for the first two, so it'll be 999.37. Let's go see what we actually got. So here we are in Knoxville, Tennessee. You can see the actual location right there. It's recorded on the GPS. Here is the reading on the scale, 999.36. And here's Blue Marble Science, my witness for this. Now, as you may recall, what was the predicted value? Looks like 999.37 grams. So that's pretty close. Now the question becomes is this a one-off? Is this just one particular reading that seemed to match my globe predictions? Well, let's go ahead and have a look at all of them. All right, so basically here's what we have. And I'll put a link to this chart in the description so you can download it and review it yourself. Now here is the initial calibration in Mount Pleasant, 43.6 degrees north. So that's reading 0 because it was calibrated to 1,000 grams. Now notice that as we go south, the weight begins to drop. And this is the raw amount that it drops. Now, here are the latitudes for the southern trip. Here we are in Mount Pleasant, then we go to Dayton, Lexington, Knoxville, Atlanta, and down to Panama City Beach. Here are the latitudes. Here are the measured weights along that trip. And here are the changes from 1,000 grams. And here's the predicted weight based on Walter Bisslin's calculator. Now, you'll notice that, obviously the calibration weight is the same. We're pretty close. Pretty close. Here's the Knoxville one, pretty close. And then we get down here to Panama City Beach, and we're quite a bit off. And you can actually look at the error rates here. So this one is kind of a bad reading north of Dayton. And this one down in Panama City Beach is a little bit of a bad reading. We had a lot more luck going north. So here we are again at Panama City Beach, and we calibrated to 1,000 grams. Then we began to head north. Here are the latitudes and the locations. Here are the measured weights. And here are the predicted weights. Now, as you see, we're very close on these. As a matter of fact, we were within 0.02 grams of the predicted end weight in Mount Pleasant, Michigan. Now, what's very interesting about this is it seems to match the globe prediction very well. Now, again, these are two sets of measurements on two routes, one going north to south, one going south to north. They're approximately the same longitude, and they change by the same 13.5 degrees. Now let's go ahead and have a look at a little bit more data, and that is the data from Critical Think. And again, multiple people made these measurements in the north and the south hemisphere, and on different sides of the Earth. So this is a much better test. So let's go ahead and see what his data shows. Okay, let's go ahead and go over the raw data and compare it against the models. So this is Critical Think's data. Now he'll present this in more detail, but let me just kind of run through it real quick. Now what you'll notice is that there's certain lines right here. This blue line, this is a flat non-rotating Earth, and it's marked as such up here. The purple line is a rotating sphere. The brown line is a non-rotating sphere. And the green line is the rotating spheroid, which is the WGS-84 model, which is our current model of the Earth. And as you can see, all of the data is plotted out. And you can use this key to see whose data there is. For example, my data is kind of in this pink color. Now you'll notice that all of our data tends to go along this green line. That's the only line that really fits the data. Now there are a couple of off points, like this one right here, which is my arrival weight in Panama City Beach. That's that 0.43 or 47 gram error. Well, let's go ahead and do a quick error analysis of this. Now here's my data isolated out and compared to a rotating spheroid WGS-84. That's this green line right here. So the blue dots are the trip going north, and the green dots are the trip coming down south. Now you see that one there is really kind of an outlier. The rest of them are all clustered right around this line. Let's go see one other bit of data that he got. Now here we have the dark blue line is the rotating WGS-84 spheroid. And then all of the data points from all of the investigators, both northern and southern hemispheric, are plotted out. Now, as you can see, there are a couple of dots that are definite outliers. There's my southbound Panama City Beach number right there. But the rest of them are all well within a 3 sigma match for the predicted line. So the bottom line is this. The data that we got on weight versus latitude matches one model very well, and that is the rotating WGS-84 spheroid, which is our current model of the Earth. It does not match the flat Earth. Now, if you look at the predictive ability of the WGS-84 rotating spheroid, it's over 98.4%. That of the flat Earth is 0. So, quite frankly, this is conclusive evidence that we're on a rotating spherical Earth that corresponds to our model WGS-84. Well, my findings are very conclusive, and when combined with the findings of other people doing it in different parts of the world, they all match. This is conclusive evidence that we live on a rotating spherical Earth. However, there are some science deniers out there that are trying to find all sorts of excuses as to why this data turned out the way that it did. Now, the cornerstone of their assertion is that gravity doesn't exist. Everything is relative density. And because there were temperature and altitude changes during the course of this trip, and of course the other trips, so what they're trying to do is they're trying to claim that simply changing the temperature would change the density enough to account for all of this. After all, it's only 1.5 grams out of 1,000. Okay, well, that's fine. I'm going to show you something right here. In Mount Pleasant, Michigan, at 43.6 degrees, at the start of this trip, during this calibration, it was 84 degrees Fahrenheit, which is 28 degrees Celsius. Now, if you feel that the temperature alone is responsible for these changes. Now, this assertion actually makes no sense. It's actually pretty childish. And it's easily disproven because our model predicted what these weights would be, and actually measuring those weights going north to south and south to north verified those predictions. However, just to humor them a little bit, they claim that temperature changes cause these differences in weights due to a change in density. Well, here's your chance to do a little bit of science. You recall those reference masses? There were 2 of them. I actually checked their volume by displacement in water, and they are 70 cc's or 70 milliliters apiece. So the total of the 2 reference masses is 0.14 liters, or 140 cubic centimeters or milliliters. Okay? That gives them a density of 7.14 grams per cc. Here's your challenge if you want to prove your case. Here in Mount Pleasant, at the start of our trip, it was 84 degrees Fahrenheit or 28 degrees centigrade. Given that information and given the volume of the reference masses, 140 cc's, go ahead and just give me the temperatures that these would have to be in order to account for these changes in weight. Now, I did record the temperatures at each one of these. So as long as you're between 2 degrees centigrade for each of those measurements, and you can show your math to show how that change accounted for that change in weight, you've got a case. If not, don't waste our time. This is Bob the Science Guy signing out from Northern Michigan. Thank you very much for stopping by. We'll see you again soon, and there will be a follow-up on this episode. Take care.
Mama, please make them hear me, or I can't teach them anymore. This rabbit hole's too deep for me. Feel my brain getting real sore. Bye, bye, bye. the science guy.